Math204 Section 3.1. We're getting near the good stuff. F, a complex function. A inside complex numbers, so that there exists some radius greater than 0, so the R neighborhood is inside the domain of F. So in other words, A is an interior point of the domain of F. If then the derivative of F at A is, and for those of you who have seen the epsilon delta proof of differentiation for the real numbers, this will not be a surprise. The limit as z goes to A of f of z minus f of A over z minus A. Beautiful. Or equivalently, this is the limit as h goes to 0 of fa plus h minus f of A over h. And now it's important that we are so also written as the derivative d dz of f evaluated at A, or d dz of fa, or any number of other valid things. Note in R, when we're talking about derivatives, we only have two directions for derivatives. In C, we now have a plane, and we have many possible directions, and in particular we could take spirals and things. This says the limit as h goes to 0. It doesn't describe how h goes to 0. In particular, what it's saying is that this limit has to exist regardless of how we get there, if you're thinking about curves. So your intuition with regards to R is a little not quite right here, and I haven't said that before because it makes a real difference here. In the other cases, the difference was more of a pedantic point. So lemma, if f is differentiable, at A inside C, then f is continuous at A. Just the same as for real functions. Proof. Okay, so continuity at A says that the limit as z goes to A of f of z is equal to f of A. This is equivalent to saying that the limit as z goes to A of f of z minus f of A is equal to 0. So I can times, this is equivalent, I'm going to times top and bottom. The limit as z goes to A, f of z minus f of A, and I'm going to times top and bottom by z minus A over z minus A. This is talking about the limit as z goes to A of f of z minus f of A divided by z minus A. Times the limit as z goes to A of z minus A. This is equivalent to saying that this is equal to equals 0, equals 0, equals 0. And so what we have here is that f dash of A, and that's A minus A, has to equal 0. So what does that tell us? If the derivative exists, we know that that has a limit, and that's f dash a. We also know that this limit has to exist. Then we know that this is true, we know that that is true because these terms will cancel, and since we know that this is true, we know that is true. Bingo. The proof assumes that this limit exists. So this is not an equivalence that continuity and differentiability is the same. This is just a series of results that say that continuity is equivalent, can be derived from this expression if you assume that the derivative exists. Now, just like every other result in which we've been working with limits, we have a theorem that describes how limits behave with each other. If f and g are differentiable, at z inside the complex numbers, then so are, or the following are true. It's probably better. The following are true. One, for all numbers inside the complex numbers, alpha times f is differentiable, and the derivative of alpha times f at z is equal to alpha times the derivative at z. 2. F plus g is differentiable, and f plus g derivative evaluated at z is equal to f dash z gz plus fz g dash z. 3. F over g is differentiable, provided that g of z is not equal to 0. This needs to be defined, so we need this. And so we have the quotient rule. F dash g derivative evaluated at z is f dash z g of z minus f of z g dash z divided by g of z squared. Alright. Sorry, normally I would put the multiplication, so the multiplication is differentiable, and, well, quotient, product rule. The product differentiated at z is equal to, oh my goodness, how did I get that wrong? I'm not thinking about it. F dash z plus g dash z, of course. And this is f dash z g z plus f z g dash z. Yes. Sorry about that. And 5. If f is differentiable at g of z, then f composed with g is differentiable at z, and the derivative is, the derivative of the composition at z is the derivative of f evaluated at gz times g dash z. Pretty easy. Proof. Mostly left for you. I mean it. You have to fight the confusion. You have to do some work if you want to get this. You have to sit down and do the proofs. And they're left for you. I'm going to do the product one for you. Fg derivative at z is equal to the limit as h goes to 0, f g z plus h minus f g z over h. So this is the limit as h goes to 0 of f z plus h g z plus h minus f z g z over h. This is the standard telescoping thing I've been talking about for ages. f plus g minus f of z, g z plus h, plus f of z, g z plus h, minus f of z, running out of paper, gz divided by h, which is equal to the limit as h goes to 0 of, and we split stuff up now. Well, there's a g z plus h, gz plus h. This is f z plus h minus z over h, gz plus h, plus the limit as h goes to 0. There's an fz, there's an fz. Ooh. Fz gz plus h minus gz over h. And since the limits of the various terms all exist, this is f dash z gz plus g dash z f of z as required. Do the rest, I implore you. If you're having problems with epsilon delta proofs, you have to just start. You have to give it a go. You have to do them. It's really, really, really important. To learn maths, you have to do maths.